I'm Tim Ventura, and we're joined today by Brandon Q. Morris, a best-selling author, physicist, and space specialist. Brandon is the author of several best-selling science fiction novels, including the Enceladus series. Brandon has a master's in physics from the Technical University of Dresden, and in past roles has worked as an editor on several science, technology, and computing magazines, as well as publishing a number of specialized technical books. Brandon is a member of the Science Fiction and Fantasy Writers of America and the Mars Society, and joins us today to talk about big ideas from the world of hard science fiction. So, Brandon, welcome. And today we are talking about wormhole communications. But before we get into that, I want to go into your background a little bit. Brandon is a pseudonym, and while I am not going to reveal your secret identity, I am going to point people towards your website, which is at hard-sf.com, where you've got hundreds of articles and links to dozens of books that you've written. So what are some of your favorites? And in terms of where people start, should they begin with your best-selling Enceladus series?
Yeah, thanks, Tim, for the invitation. I'm happy to be here. Generally, my books are all set in the same universe. So what happens in one has consequences for those that are set later in the same universe. So there are many starting points still. If you start with the Enceladus series, you will have the best background for all the others. I tend to either put an astronomical or physical phenomenon into the center of my novel. So there are some few that I also like a lot, like The Disturbance, that goes very much into quantum physics, if you prefer that, or even Mobius, if you fancy mathematics. I really think mathematics can be fun even in a science fiction novel.
Wonderful. And so the title of your website, as well as the subject material, the content that you write, is hard science fiction. So Wikipedia defines that as a category of sci-fi characterized by concern for scientific accuracy and logic. They list Arthur C. Clarke, who is a personal favorite author of mine, and Larry Niven, I love Larry Niven, as examples of hard science fiction. So I'm wondering, in terms of popular TV, do Star Trek, Star Wars, Stargate, or the Battlestar series, do any of those qualify as hard SF?
Well, it's actually more like a spectrum, I would say. It's not either that or not, but it's between. So actually, there's a website called TV Tropes who has developed a scale for the hardness of sci-fi, the most scale, which goes from 1, which means the science is in a genre only, to 6, like real life or non-fiction. Star Wars in this scale is classified as most 2. Star Trek is a bit harder at most 2, and Battlestar Galactica is already most 3, like physics plus. To compare that with my novels, they are either most 5, so-called speculative science, or most 4, one big lie. I usually prefer most 5 because it's more physics in there, but to get further away in science fiction, further away from Earth, that is, you sometimes need some big lie, like the idea to be able to fly faster than light.
Well, that's a good point. And I think, especially in terms of Star Trek and a lot of science fiction like that, a lot of the ideas were added to those as plot devices, right? The character needs to be able to get from point A to point B very rapidly so that the story doesn't fall apart. And so they fabricate something or they fudge on the physics. And that's kind of a constant challenge, I think, for all of us, because we pick up and learn things incorrectly and we pass that along sometimes as well. And then we have to kind of take 2 steps back and say, wait a minute, this was something that, came out of sci-fi as opposed to being real. I mean, offhand, it sounds like anything with the title star in it is not hard science fiction. And there's probably basically no hope for anything in the Marvel or DC cinematic universes, right?
That's actually a quite interesting pattern, and I don't really know of any title that contradicts it. But sure, Marvel or DC are clearly most level one. There's one interesting fact in Battlestar Galactica. If you take the original series, it's more like fantasy, but the newer one is actually even harder. So, for example, they have less sound of battles outside in the vacuum, where you can have no sound at all. So they reduce that at least in the new series.
Yeah, yeah. I actually I'm a big fan of all those series. Battlestar was interesting. When they introduced that, another thing that they used was what they called a shaky cam, right, in the space battle scenes.
Yeah, yeah,
And
yeah.
from what I've heard, they actually had to stop using that as much because it was making some viewers feel sick. They were complaining, but
Mhm.
I loved it. I thought, this adds an element of realism to these space battle scenes. Well, so our topic today is your article entitled Tiny Wormholes May Be Usable for Interstellar Communication, which was published in the Debrief and based on a scientific paper entitled Traversable Wormholes in the Einstein-Dirac Maxwell Theory by Jose Luis Blázquez Salcido, Christian Knoll, and Eugene Radu. So I'm wondering if you can give me kind of a high level overview of the idea that was in this scientific paper and what inspired that about you to write this article.
Yeah, generally, I always look for inspiration for my novels in the newest research papers. And probably not many people know there's a great website called Eurik Alert, where scientists and universities share and publish these. So that's where I found that paper as well. And it was especially interesting to me. We already talked about that because for my novels, I need communication between the heroes, and to hear about this way is quite helpful. So what is it about? So I think we have to start with wormholes in general. First of all, they are solutions to Einstein's equations of general relativity. So that being said, being a solution does not mean they exist in reality. We didn't found any so far. But it means they could exist. They are not, again, the general relativity is not against it. But if you want to send anything through it, that's what we know. The gravitation of the traveling thing, the traveler caused by its mass, would cause the hole to collapse. So that's for sure. But it can be solved if we fill the wormhole with negative mass or negative energy, which is basically the same. So the hole, one could say, doesn't feel the real mass of the thing that's traveling through it anymore and does not go away. So, but the bad thing is we need really lots of negative energy, like several star masses. And most physicists don't even think negative energy exists in the first place. So that would be really hard to create a wormhole with negative energy. Now, coming to the paper, the authors are creating a wormhole by involving charged particles like electrons, and they show that if there is a high ratio of charge to mass, this wormhole could be stable enough to let charged particles pass through it without collapsing. So electrons are perfect for this, of course, because they have a lot of charge, one charge, in a very small mass.
Yeah. And again, this is so exciting. It goes to what you originally said about negative mass. And I think the same applies to the Alcubierre warp drive, right? The requirements for negative mass, as you've said, were several stars worth of energy, which is just, impossible, right? But if they're able to substitute charge for that, even in a nanoscale wormhole, then all of a sudden that opens the door to a world of possibilities. So I did want to clarify on one point that I got confused on personally. Electrons have negative charge polarity, which is not the same as negative energy. So what makes wormhole travel possible, the way that it's described in this paper, is the charge to mass ratio of the electron, which is very high, and not the actual charge polarity itself, which is still positive energy, right?
Absolutely, yeah. Negative charge is what we know as a very usual phenomenon if we power all our electric devices. So it's clearly positive. Negative energy would be something that takes away energy from us. So it's even hard to imagine how negative energy could exist in the first place. In the calculations of the researchers, they really focus on electromagnetic interactions, and that's where charge plays a role, and that's why a negative charge in their model can keep the simulated wormhole open. So in this case, it has the same function as the negative energy has in the full model. The question is, would their model also work in the full situation? And the scientists are pretty optimistic that that's the case.
Well, so in addition to electrons, I believe you could also send photons through this, right?
The big problem with sending photons is, yes, you can do that. Electromagnetic waves, which is another name for photons, can move through this kind of nano-wormhole if you keep it open. So to keep it open, you would have to send electrons as well, because they are needed inside. So you would basically shoot both photons and electrons through it, and then it should work.
Aha. Okay. Okay. So maybe there's the potential for multiplex signals as well then. So this is a really exciting idea. This is not the way that this paper is written, what's called an ansible. And that's an idea that Ursula Le Guin came up with, which is a fictional device capable of near instantaneous or faster than light communication. As I understand things, and I believe this was actually on the Physical Review, the website actually where the paper was listed, what they were saying was, to the observer going through the wormhole, the electron, it would be near instantaneous travel, but to an outside observer, it would still obey the speed of light, right? So you could send signals to the signal itself, it would appear to be instantaneous, but it would still take as long as it was, required to get to its destination.
Yeah, absolutely. The electron itself does never go above the speed of light. Even if it needs only 10 seconds or so to reach the target, which is from us, maybe 5 light years away, it still needs only 10 seconds and flies with its own speed. So that's not a problem for general relativity. The more of a problem, and that's something that makes an Ansible hard to construct, is the observer, like the sender is an observer as well. In this case, for the observer, it might look that it needs still 5 years to reach the target in 5 light years. So yeah, but that's still in discussion very much in physics.
Well, yeah, and one of the things that I've been really excited about lately is Leonard Susskind and Juan Maldacena's ER equals EPR conjecture, which essentially suggests that the Einstein-Rosen and the Einstein-Podolsky-Rosen are the same thing, right? If that's the case, entanglement and wormholes may have some corollaries, and I was hoping that there might be instantaneous travel. But from what I understand, you're saying that we won't really know the details of something like this until we have a quantized gravitation theory. Is that correct?
Yeah, that's the problem. The ER equals EPR conjecture is a really fascinating idea, and it's to the right direction, I would say, because it connects quantum physics and general relativity. But that's what nearly all theoretical scientists right now are trying to do, to create this connection between these two areas that seem very much disconnected right now. So as soon as we have this theory, we will know if ER equals EPR is correct or not.
Ah, okay. Well, so I want to mention a fictional novel, The Light of Other Days by Stephen Baxter and Arthur C. Clarke. For me, this was an inspirational novel. I think they wrote this in 2000, 2001. And the actual idea, they were talking about privacy at the beginning of the internet. And their plot device in this case was a nano wormhole or a quantum wormhole that was just large enough to pick up a few photons, but they envisioned being able to use this as a camera that would be able to basically see anything anywhere. Now, in their case, you only had to create one end and you could remotely reposition the other end of it to use it as a camera. So there was a lot of fiction involved with this, but something like that could be possible potentially, right? Being able to send photons through this. Do you think you might be able to create some kind of a camera for space exploration?
Well, it's a fun idea on one side and quite reasonable as well. If we follow that model based on the paper you mentioned, the problem is we still need electron transfer through the wormhole to keep it open. So like with the camera as well, you need to provide electrons for a normal camera, and you need to provide electrons for this camera as well. The interesting thing is we might not be able to move the other end of our camera as is described in the novel, but on the other hand, there are already a lot of entangled particles in the universe. So if we find a particle here next to us and find the entangled partner somewhere else, then we could use it as an existing camera. This kind of wormhole as an existing camera, we might be able to look light years ahead with this one.
Yeah, big ideas and exciting ideas. And it feels like we are right on the verge of learning so much more about these. The other thing that occurred to me was if you can send or if you have to send electrons through this wormhole to keep it open, it seems like not only can you send a signal of some kind, but you can send at least some type of power. And so potentially you might be able to use this to power, who knows? I mean, remote computers, remote transistors, remote space probes, something along those lines. Do you think that that possibility is there, or is it too little to be
That sounds quite
practical?
interesting. Yeah, it sounds quite interesting. The problem might be that we don't know the energy balance of the whole thing yet. So it must be positive, of course. So it really depends on the situation. But really, we want to send tiny probes to like Alpha Centauri, and it would be really useful if we were able to provide power to them, even in the interstellar space where they cannot use solar cells or other receivers for energy anymore. So if that would work, it would be really helpful for space travel, with this kind of probes.
It's intriguing. The final idea that occurred, to me, this seems a little outlandish, but actually, I think this may have been at the end of The Light of Other Days. They come up with this idea of dropping the other end of the wormhole into the sun. And that's an alternative to having to create fusion energy, is literally just pulling it directly from the sun through a wormhole. And again, a tremendously big idea. But when I read that, I thought, that's incredibly intriguing.
Yeah, energy is basically photons. So it would work in some way. The problem might be normally in quantum physics, we want to cool down everything and to keep it from collapsing. And the sun might not be very favorable in this aspect. So we have to see, having the theory of everything, and then we can calculate if it works or not.
Well, do you think that communications of this type, wormhole communications, that may not have the tremendous power requirements that are associated with radio, might be preferential for interstellar communications? And the reason I ask is I'm wondering about the Fermi paradox, right? Which is the Drake equation suggests that there may be something like 10,000 intelligent advanced species out there, and yet we're not picking them up. And there could be many mundane reasons for that. But one of them that I'd wondered about was maybe they're using something better. And that could be potentially something like entanglement or wormhole communications, where it just doesn't have the broadcast power requirements.
they could use that, but we would still receive electrons or photons. So, and that's what we are looking for. Maybe we are not yet looking in all the right wavelengths they might be using. So we have a lot of telescopes in different wavelengths, but normally these are attuned to wavelengths that are somehow interesting for astrophysics, of course. So it's the main reason they exist is astrophysics. So maybe there are wavelengths that they are using that are not suitable for astrophysics. On the other hand, if I were a faraway civilization, I would try maybe a wavelength where I'm pretty sure that the others are listening to. So maybe I would choose a wavelength that's connected to an astrophysical phenomenon. So yeah, it's hard to say what they would be doing, but still it's photons and electrons, and that's something we can easily receive right now.
Wonderful. Wonderful. Well, Brandon, let me thank you so much for your time. And I want to remind the audience that, like our discussion today, all of these ideas came out of one article that you had written on your website. You have so many more articles, and you have written dozens of books. I mean, there are so many, I actually thought about listing them. And then I got about halfway down and I said, there's no way I can read all of these titles. So you are this tremendous producer of hard science fiction, which is personally my favorite type because it's the kind of thing that can become real, you know? So let me thank you so much for your time. I want to urge people to visit hard-sf.com. Check out your books and articles. I'm going to put a link into the YouTube show notes for that. And let me close by asking what your current projects are and if you have any new books coming out soon that we should keep our eyes open for.
Yeah, I just finished a series that revolves around the Fermi paradox that you already mentioned. So the idea, why are there no civilizations around us? So what that makes them collapse, maybe? And this novel is set in the dark cloud LDM 63, quite near to Earth. And in my universe, at least, it's humankind's first interstellar voyage. So you get some concepts of interstellar travel as well.
Wonderful. Thank you again so much for your time today, sir.
I thank you. Very interesting question. Thank you.